In 2013, the Nobel Prize in Physics was awarded to Peter Higgs and Francois Englert for the theoretical discovery of the mechanism which gives elementary particles their mass. This theory was confirmed in 2012 by the discovery of the fundamental particle responsible for the mechanism. This particle is known as the Higgs boson, and its discovery greatly impacted our understanding of particle physics and the nature of the universe itself. Before we get into the Higgs discovery, we'll first discuss some background information about the standard model of elementary particles, the smallest particles that make up the known universe. The standard model includes fermions, which make up physical matter, and also bosons, which are responsible for the forces we experience every day. The strong force, which keeps the nucleus together, is mediated by gluons. The weak force, responsible for particle decay, occurs by W and Z bosons. And finally, the electromagnetic force allows for friction and magnetic attraction and is mediated by photons. But what about gravity? It's observable on the largest scale and has perhaps infinite range, but how does it work? We have yet to find a graviton, and Einstein's theory of relativity doesn't mix well with quantum mechanics. We know gravity is dependent on mass, but what determines the mass of particles in the first place? Peter Higgs proposed there must exist everywhere a field that interacts with specific particles to give them mass, much like a magnetic field affects charged particles. This field was dubbed the Higgs field. In 1964, Higgs, along with Francois Englert and Robert Brout, published the theory of the Higgs field independently from each other. It was a plausible theory, but it needed to be proved. It also required the existence of scalar fields, fields with magnitude but no direction associated with them. The theory did not gain much initial support. However, the 60s and 70s were big decades for particle physics, as new fundamental particles were being discovered quite often. Higgs's theory had correctly predicted and described the particles being discovered, so physicists gradually became convinced the Higgs field theory might be true. If the field did exist, they thought, there must be a particle associated with the field responsible for the Higgs mechanism, which gave particles their mass. This sparked a 40-year hunt for the new particle, which was called the Higgs boson. The Higgs boson required massive amounts of energy to be observed. To obtain this energy, physicists needed to use particle accelerators to smash particles together at nearly the speed of light. About 1 in 10 billion of these collisions would create a Higgs boson, which would immediately decay via predicted decay channels dependent on the Higgs mass. Two of the clearest decay channels were the Higgs decaying to a W boson loop and then to 2 photons, and the Higgs decaying into 2 Z bosons, which would then decay into 4 leptons. Of course, random other decays would produce the same products, so the number of decays found at specific energies were compared to the expected background noise. Then statistics were used to determine the significance of an increased number in decays. Using these methods, accelerators were built in numerous countries to confirm the Higgs's existence. In 2003, the Large Electron-Positron Collider at CERN determined the mass of the Higgs should be greater than 114 gigaelectron-volts. To get more energy, CERN built the Large Hadron Collider using the 27-kilometer LEP tunnel, which would have energies of around 10 to 20 tera-electron-volts. It cost billions, took years to build, and required thousands of physicists and engineers to dedicate years of their work, with no guarantee of success. In 2008, the LHC started test runs, but a problem in the superconducting magnets caused major damage. After a year of repairs, LHC began testing at 7 tera-electron-volts. 2 separate detectors, ATLAS and CMS, took data for 2 years. By 2011, ATLAS determined the Higgs must exist in a small window around 125 gigaelectron-volts. In 2012, energy of the LHC was increased, and again a significant bump in products was found around 125 gigaelectron-volts by both ATLAS and CMS. On July 4, 2012, the findings were shown at a conference with Higgs and Englert in attendance. Brout had passed away a year prior, but would have been glad to hear that they had discovered the Higgs boson. The Higgs discovery had massive impacts on the scientific community. It explained the origin of mass, completed the standard model, proved the existence of scalar fields, and opened a new foundation in particle physics to build upon. Is the Higgs a possible link between dark matter and regular matter? What does the Higgs's energy imply about the stability and future of our universe? Is there more than one type of Higgs particle? These questions and more are now being investigated. In this way, the Higgs discovery has opened a realm of possibilities for our study of the universe.